All right, chapter 15 talks about refraction of light. We've learned about refraction already in physical science, and refraction is the bending of a wave when it enters a new medium. Okay, so if we're talking about a sound wave, right, if it enters a new medium, that sound wave is altered. Light is a little bit easier to kind of show this refraction, and we're going to explore light refraction in chapter 15. Since light has wave properties, that must mean that light also refracts just as sound does. So light refracts as it enters a new medium, and that's what refraction is. So light refracts. A good example of refraction with light that everyone is likely familiar with is when you look at a straw in a glass of water. So if you look at the diagram on the right here, the straw appears to be bent or disjointed. So an example of refraction of light, a straw in a glass of water that appears to be bent or disjointed. So all of you have had this experience one way or another. You look at a pencil in a glass of water, or you look at a straw in a glass of water. Now I don't have water in my water bottle here, but I just finished it up. But here's a diagram here for you to see. That's probably a little bit easier for you to see anyways. You've seen this before where the straw or the pencil or the pen or some object that extends into the water and also into the air looks different. It looks maybe a bit bigger. It maybe looks disjointed. As you get it closer to the edge of the glass, it sort of kind of spreads out and warps a bit, right? And all this is happening because light that's traveling to your eyes from up here is coming only through the air, right, to your eyes. Now down here, actually light is traveling from air through glass and then back into the air, so it doesn't look too much different. But here, the water and the glass combination definitely bends the light in a certain way, and so you actually see what looks like a different object. Now, you all remember looking into convex and concave mirrors, how the image sort of gets spread out a little bit, or it kind of narrows in, right? That's the sort of thing that's happening with the light rays here. So light bends when it enters a new material, such as a glass block or water. When light travels from air into glass, most of the light continues through the glass. So most of the light continues into the glass and through the glass, but some reflects. This is called partial reflection and partial refraction. So we have part of the straw refracting, the light rays are coming out and bending, and some of the light rays are bouncing back in. When you look at a glass, and the next time you do, and I might fill up my water bottle here with my straw to pass that around for you, but when you look at that, you will also see that you can see a faint image of the straw inside the water bottle or inside the glass. And that faint image of the straw is part of that partial reflection. Okay? Partial reflection and partial refraction. The incoming ray of light is called, the incoming ray of light is still called the angle of incidence. So we still have an angle of incidence. The point that the light hits the new material is the point of incidence. And I think we've put that in a diagram previous. The reflected ray is still called the reflected ray, but now there's a third ray that we need to examine. So we've only examined, this and this up to now. But now we need to examine the refracted ray. So as the light travels through the border of the medium here, from one medium, in this case air, into water. So this is the refracted ray. Reflected and refracted. Okay? Okay, they're different. One is bent and one is kind of a bounce off. That's the difference. So the third ray that travels into the material is called the refracted ray. All right. Now, if this boundary here between air and water was, if there was nothing extra here, like no extra reflective film or anything like that, then we have a slight partial reflection, and that would be represented by this ray. But most of the light would go through, and that's what we see when we look at a straw. Okay, so on. All right. The interesting thing is that if you reverse the refracted ray, so what I'm talking about is if this was the incoming ray of light now, okay, if that was the incoming ray of light, then it would follow back the exact same path. So it would actually travel right here as well. Okay? So this angle of refraction is dependent upon the material. Okay? So in water, if you have a light ray coming through water and into air, it's going to be refracted in a predictable way. The same that if a light ray was coming from air into water, it's refracted in a predictable way. So this is called, when light travels in the same path in both directions, it's called the principle of reversibility. It's important also to note that this is still the angle of incidence, but we have a new angle too that we're going to be dealing with, and that's the angle of refraction. So I'll just get rid of this black line. This is the angle of refraction. Again, it's always measured from the normal, just like this one is, from the normal to the light ray, and this one is from the normal to the light ray as well. Okay? Angle of refraction. So I talked earlier about the fact that each material has sort of its own properties when it comes to refracting or bending light. And that is called the Index of Refraction. Let's just read this paragraph. It says, an index is a list of information. In the back of a book, the index gives you page numbers where you can find particular pieces of information. With light, we have something called the Index of Refraction. So if we put those two things together here, the index is sort of a list of information, okay, and the list of information regarding refraction or refracting rays, or the angle of refraction. So that's what index is. It sort of gives us information on different materials and how it refracts light. The index of refraction, again, is a list of materials with a number. So it's a list of materials with a certain number. And what does it show? It shows how the speed of light in that material compares to the speed of light in a vacuum. So we'll just unpack that statement just a little bit here as you copy that out. The speed of light in a vacuum is the fastest that light can go. Okay, that means there's nothing inhibiting light from traveling through it. In different materials, light actually slows down. That's why we have refraction. That's why we have bending of light. So in a vacuum, there's no air, there's no substance at all. It's been evacuated. Everything has been evacuated. And so light has a speed in a vacuum. But when it travels through air, it actually slows down a little bit. When it travels through glass or water, it slows down even more. And this contributes to the bending of light. Okay, so what does the speed of light have to do with refraction? Well, the reason that light, or in fact any wave, bends when it enters a new material is that the velocity of the wave changes in that material, and that's what I was just explaining. So the reason that light bends is that the velocity of the wave changes in the material. The reason that light bends is that the velocity of the wave changes in the material. Okay, so there's that picture of the glass again here for you to look at while we talk about this. So the index of refraction is basically a ratio of how the speed of light compares to the speed of light in a vacuum. So how the speed of light in that material compares to the speed of light in a vacuum. It's a ratio, really. Okay, so it's a ratio. N is the index of refraction in this little formula right here. This is the formula for calculating the index of refraction. N is the index of refraction. C is the speed of light in a vacuum, which is this value right here. So the fastest that speed could possibly go is 3.00 times 10 to the 8 meters per second, or 300 million meters in 1 second. And we talked about that, right? When we first talked about light, how it goes around the Earth 7+ times in 1 second if it could actually travel in a straight line. If you shone your flashlight and it could go all the way around the Earth and without hitting anything or stopping, in 1 second, if you were able to trace that path of light, it would go around, about 7 times in a second. Really fast. So in air, it slows down slightly. Not too much, but very, very slightly. And in certain chemicals, in glass, in water, in diamond, it slows down more and more and more. And so V is the speed of light in the material that we're talking about. Okay? Now before you launch in this question, I don't want you to start this question yet. I'm going to ask you to look at page 466. There's a chart of the indices of refraction. Indices is the plural word for index. So there's many indexes of refraction. Okay, this chart is very similar to the one you have in your textbook. It might not be exact, but let's take a look at this chart up here, and let me show you what this means. So in a vacuum, the index of refraction is 1. Why is that? Because the value for C and the value for the velocity of air in that medium would be the same. And so 3 times 10 to the 8 divided by 3 times 10 to the 8 is exactly 1. Right? Now air is the next on the list there, and its index of refraction is 1.0003. So that's pretty much the same, isn't it? It's pretty much the same. What that means is that light doesn't slow down much if it's just going through air. It doesn't slow down much at all. Now if light goes through ice, okay, then it actually slows down quite a bit comparably, doesn't it? You have a little bit larger index of refraction. So that means that when light travels from air into ice, it slows down. Okay? The actual speed of light slows down. Now, it's still pretty quick, but it slows down. Water, a little bit, slows down a bit more. As we move down the list, you see these ratios go up, the indices go up, they get larger, so that means that that this V is getting smaller. And so diamond has a very large index of refraction. Look at how it jumps here. And that's really important if you're talking about it. We're going to, when you get into the applications here in this chapter, and one of them is why diamonds are so sparkly, and it's because of the high index of refraction. When light enters a diamond, it basically slams on the brakes, and when it slams on the brakes to enter a diamond, and if it's coming at an angle that's not exactly 90 degrees, if it's on a bit of an angle, then when it slams on the brakes, it actually the light ray actually spreads out, and that's why you get the sparkling of the different colors and stuff. If you have a diamond, you can see the different colors on the ceiling when someday maybe you guys will own a diamond, big diamond ring maybe, but anyways, that's why. It's because the diamond material is so dense, but yet transparent, so you can see the light slamming on the brakes when it comes into a diamond, and some neat stuff happens. So we'll get into that a little bit more later. All right. So on page 466, why don't we take a look at, let's just do a little example here, page 466, the sample problem. Okay. The sample problem on page 466 says this: the speed of light in a liquid, in a particular liquid, that's going to be V, and V could stand for velocity, right, is 2.25 times 10 to the 8 meters per second. what is the refractive index? So A says, what is the refractive index? And that really is the same as the index of refraction, okay? AKA index of refraction. All right, so can we figure that out? Pretty easy, actually. You remember your formula. N, that's the index of refraction, or the refractive index, equals C divided by V. Okay, C divided by V. And so what do we have? Well, we have V right here, and we always have C, right? C is that constant, speed of light in a vacuum. So then you go N equals the speed of light in a vacuum is 3.00 times 10 to the 8 meters per second. The velocity in this medium is 2.25 times 10 to the 8 meters per second. Make sure your units line up, of course. If it's in a different unit, like kilometers per second, you're going to have to do that conversion from kilometers to meters, for example. And then we can find the index. So we do that on our calculator, and then we'll get the... All right, so you do that calculation, you get N equals 1.33, repeating, okay? We got three sig figs there, so we'll leave 3 sig figs for the index, and that's what you see. Now, if we go back to our chart, so do you see that index on the chart anywhere? Oh, right here. So I guess what we found out is that in this question, the material, right, is water. So the material is water. I think that might be what your second question is. The material is water. Okay, so we just went back to your chart there and found that out. Okay? Any questions? All right, so I'll give you your assignment here, and it's on page 467, number 1 to 3.